All right, and we're good. All right, cool, no worries. So let's start with any questions. So as far as homework and lab, what I'd like to do in general is grade them after you turn these things in before the next class period, and then give you some comments and feedback. And then the following class period, right, we can actually talk about them. I'll go over things that I noticed across multiple submissions, and you can ask about, you know, things that you're still unclear about and so on. So generally, you know, if you turn stuff in on Thursday, I'll plan on talking about it the following Tuesday. But if there's anything pressing that you want to talk about already on the homework or the lab, or on lab 2 or on homework 2, and remember homework 2 is due on Tuesday, let's go ahead and talk about questions right now.
I have a question that I think you mentioned last lecture, and I can't remember exactly what it was.
Okay.
You mentioned, like, if this were basically like, see, there's a hashtag include pick
18f1220.inc, yeah.
And then you're able to access the, like, just say port A.
Correct.
Does that go with column 1, like the defined statements?
I believe the number sign include. Oh, I thought I knew until I started to answer your question. Let's take a look. So, if you look at Lab 7, which is posted, there's some sample code in there that does a whole bunch of things, including the include. So the include does not start in column 1. There's no number sign in front. So it's just include.
Okay, thank you.
Mm-hmm.
Why is there a .inc, do you know?
That's just the extension on the file.
Okay.
And it's literally just a file sitting somewhere in the file system under the MP Lab main directory, and every processor that is available has an include file associated with it. So let's let me see. So on my system, right, this is what that directory has, and these are just all the different include files for different kinds of processors. So you know, most of these define something called port A, and port A has different values. On this P12F609, port A is set equal to 5. On this P12F1822, port A is set to something different. It varies from processor to processor. Right, and on our processor, the 18F1220, port A is hex F80. So the nice thing about this is, you know, as I've said, if you write code for, you know, this processor that we're using, and then you decide you want to use that same code on a different piece of hardware, all you have to do is change that one statement, that one include file, and now, you know, when you say port A, it'll refer to whatever the file register number is for port A on that new piece of hardware. And so it's a nice way to be able to reuse code without having to, you know, go back and rewrite it and learn how the new processor is set up differently and so on.
Have some portability for assembly code.
Exactly, yeah. And that's why we do, you know, include files in C, because on this machine, particular type of variable might, you know, have a certain length. On another machine, it might have a different length. And so we just say number sign include standard IO.h, and it sets all of that stuff up for the particular machine we're compiling on. Other questions?
Yes.
Yeah.
I know I emailed you about EQU, but what I really wanted to know was what does EQ and U stand for?
What does what stand for?
EQU. It's
EQU, yeah.
on question 13.
Yeah, so EQU is kind of like a number sign define. It's a way to say this symbol is equivalent to this address.
So
And
they don't have any specific words attached to the letters? Like echo,
oh, it
quality,
stands for
amplification?
equivalence. Equivalent.
Thank you.
Yeah, at least that's how I think of it.
That was really the question that I had.
Oh, okay, yeah. Yeah, it helps to have like something to associate it with. And let's see if I can looking for something, a good resource here.
Could we also go over 9? Because I know we went over, like, the A number 0 and 1, but I had some trouble interpreting that into assembly language.
All right,
I
so
think I got it right, but I'm unsure if I really got it solidly.
okay, so question 9: convert the following to assembly language. So you one in particular you want to look at?
Yeah. How about OX2997?
All right. Hey, my camera died again because you can't see what I just wrote. It's some combination of starting Zoom, starting my screen recorder, and I don't know what else that makes my camera fail suddenly. Good. Bonus. All right, so OX2997. So let's take a look at the table 20-1. So let me hop to my quick reference guide. So 2997. So what's a good first thing to do when trying to convert these into assembly language?
Convert the hex code to binary.
Convert the hex code to binary, because all of these bit patterns are done in binary. And you know, the 2, if you know hex, you can pick that out, but the 9, you know, we're only going to use a few of the bits from that second digit. So let's just write this out in binary. So 2 is 0010. What about 9? How do we do 9 in binary? 1001. Good. 8 plus 1. And then 7.
0111.
Excellent. All right, so now you just you hunt, right? You look for a 0010, and so these first 2 match that pattern, and we're looking for a 10 over here, so it's neither of these. So go on for 0010, and you know, you could sort this. You could find a table where this was sorted by binary code, and that might help. 0010, and then here's a 11, so that doesn't work. 0010, and there's a 10, and then 2 bits DNA. So it looks like this pattern right here is going to match what we're looking for. And that's an increment F instruction. So 0010, and then we're told 10DA, and then we have 8 bits of file register. That's an increment F, so we don't need this anymore. So this is an increment file register where D is equal to 0 and A is equal to 1. All right, and what's the number of the file register that we're trying to increment according to this coding of the instruction?
F97.
Yeah, so we can take these last 8 bits, that's the file register number. Well, 4 bits gives you a hex digit, so for these kinds of instructions, it's always just going to be these last 2 hex digits. Right, but don't memorize that, right? Start from here and convince yourself, oh, okay, so that's just those last 2. So this is an increment file register, hex 97. And the destination bit is a 0, so where is this going to write the result of the increment into?
Red?
So it's either going to go back into 97 or it's going to go into the W register, right? If D is 0, that's the W register. So you can put a comma 0 or you can put a comma W. W is a shortcut for 0. But increment the contents of this, but leave 97 unchanged. Store the incremented value into W. And homework 1, we're not dealing with the access bit yet, but if we were, remember our little cheat sheet from last class, if the access bit is 1, then we're just writing into this file register. If the access bit is a 0, then we take the most significant bit and we sign extend it. So this would be an F97 if our access bit was a 0. So this is just a plain old increment file register 97, save the result in W.
So I got that backwards then.
Okay. And then if you want, you can check your work. So run your MPLab simulator. Let's get rid of that. And let's just put an instruction down here. Increment file register 97, comma W. Let's go ahead and build that. Oh, didn't like that. I'm doing something weird here. Oh, there we go. Alright, so there's our increment file register 97, comma W, and the opcode for that is 2997, which was what we started with. So that's one way to check your result on these. And this is not something you're going to do a lot of in life, right? Unless you're on a desert island and you're very bored. We don't spend a lot of time assembling instructions by hand or disassembling instructions by hand. We have programs to do that for us, right? MPLab and disassemblers and so on and so forth. But doing this is a good exercise in understanding how, you know, the instructions that we write get coded in a way that the machine can read, and understanding this process of going from, you know, something like this to something like that helps us understand why certain things are the way they are. For example, why we can only specify 8 bits of an operand, even though we might want to use a 12-bit address like F80 for you know, port A. It helps to do this mapping back and forth a few times. So does that make more sense?
What if you included the A bit at the end? And comma 1 for the A bit.
So we don't usually specify that, but that's what this is up here. So each of these instructions has an either comma access or a comma banked, and that gets replaced with a 0 or a 1 to explicitly, you know, indicate what we want the access bit to be set to. If we included a comma 0 to say this is supposed to use the access bank, then this would be coded with with a 0 in this position here, so it would be 2897 for the binary code. And I believe we can do that freely.
So to signify a difference in the A, we actually have to state access or banked.
Yeah, or a 0 or a 1.
But I thought you said reg and 0 are the same thing. Or are they not? W and 0?
W and 0 are the same thing, right? But if you go back to the description of these, look at the opcode for an increment F. It says the mnemonic, that's the opcode, is INCF. The operands are the file register, that's our hex 97, comma, the destination bit, that's our comma W or comma 0, and then comma and the access bit.
I'm curious.
Yeah.
If the destination is not specified, and you just have a different kind of A bit, does it still read it as like F and then a null space and A?
So if you, so I mean, maybe you could do, let's play with this. Okay, so this is the destination bit, this is the access bit. If you just specify the destination bit, the access bit gets filled in by MPLab. If you don't specify anything, then the destination bit is taken to be a 1, right? The default is to write back into the file register, and the access bit is figured out by the assembler.
So the destination definitely has to be filled in for it to read a difference in the A.
Yeah, if you want to specify the A, I mean maybe you could do something like that. I'd be surprised if it let you. But you know, let's find out.
I was kind of curious about that because I know a couple of them had like the A was 1 in these, and I was like, how am I supposed to specify that? So I actually left them open because I was uncertain.
Let's see if it likes that. Hey, it does. So putting in just a nothing F in between the commas, it took that as let's just use the default value, and the default is to go back into the file register, so it uses an F instead of a W.
Cool.
Yeah, that is kind of cool. I had no idea it would do that. And there's two extremes here, right? On the one end, we can be very kind of casual and chill about how we write assembly code and just let defaults happen, right? The other end is, you know, we specify every single thing. We do all of our encoding using, you know, the file register and the D bit and the A bit. And usually we want to land somewhere in between those. Most of the time, the access bit doesn't need to be specified, especially on this processor, because if we want to, you know, sign extend that bit, well, if we try to increment, you know, 0xF97, it's going to set the access bit to be a 0. And if we want to actually do F97, we can just say 0xF97 instead of x97, comma, W, comma, 0, right? So usually just fully specifying what address we want will cause the access bit to be set properly. And then for this destination bit, I've kind of gotten used to, I don't specify it unless I want to use the W register, and then I say comma W. But, you know, it's kind of a style thing. All right, and somebody just asked if we could go over 0x0680. So same thing, let's write it in binary. So there's 0680. And this should be easier to find because we've got 4 zeros in the beginning. and that's a fairly unusual opcode. So here's a 0, 0, 0, 0, and there's a 0, 1, and it looks like that's going to match the first 6 bits of our pattern. So this looks like a decrement file register, and I'll move this out of the way in a second. So decrement file register has the pattern 4 zeros, 0, 1, DA, and then a bunch of F's. Alright, so destination bit is equal to 1, access bit is equal to 0. This is decrement file register. And the file register is hex 80, which looks like this. But remember, if this access bit is a 0, then we're specifying a 12-bit address where these 4 bits are the same as whatever this most significant bit was. So this looks like a decrement file register F80. And the destination bit is a 1, so it's putting the result back into the file register. So that should code just as decf F80. And so let's check that. So decrement file register F80, which had replaced as port A, and the coding for that is hex 680. So that looks correct. And this is definitely the harder direction, going from assembly language, from machine language into assembly is harder because it's a, you know, many to one kind of thing. Assembling, if we know what the exact assembly language is, converting that into machine code is really finding the instruction, which we're good at as humans, right? Picking out that and then filling in the bits over here. So lab hours Tuesday, question came up on the which one was it? Let me see. Hold on. The move WF instruction. So move WF has this coding of 0, 1, 1, 1, 0, 1, 1, 1, followed by an access bit. And there's no destination bit in this coding. So most of these instructions we can specify a D bit, which says should we put the result into W or into a file register. But move WF doesn't have a D bit. And you know, the D bit would normally be right here where this 7th digit is, this 1, but it's hardwired as a 1. And the reason for that is this instruction moves the W register into a file register. If we were to specify a D bit here, and we set that D bit to 0, we'd be saying move the W register to the W register, which doesn't really make any sense. That's basically a no-op. And so instead of having, you know, a 0, 1, 1, 0, 1, 1 with a D bit here, they say this has to be a 1 for it to be a move WF. Right? Because if we put a D bit in there, putting a 0 in there wouldn't really make any sense. And guess what? If you put a 0 into the 7th bit, 0, 1, 1, 0, 1, 1, 0, you get a totally different instruction. You get this instruction right here, 0, 1, 1, 0, 1, 1, 0. That's the negate file register instruction. And guess what? Negate file register does not let you specify a D bit. Now, complement file register, that lets you specify a D bit. So does clear file register. So does decrement file register, increment file register. But negate, there's no D bit option. You cannot negate a file register and store the result into W directly. Okay, why not, right? Well, this is a design decision made by the people who architected this chip. Since we've got to move WF and we don't need a D bit on there, let's pick some other instruction to have the same bit pattern where the 7th bit is a 0 and not put a D bit on that instruction either. Well, negating a file register is not a very common thing to do. Complementing it is much more common. Negating assumes that we're working with signed integers and we're doing 2's complement, and that's just not as common a thing. And if we really want to negate a file register and put it into the W register, we can use a temporary register somewhere else, right? Negate it in that file register and then copy that into W. So we got 2 instructions for the price of 1, basically, right? We had a bit pattern, but we hardwire 7 of those bits and use it for 1 instruction, right? Move WF, and then we use a slightly different version of the hardwired 7-bit opcode for the negate instruction. So
I actually, no, sorry.
No, go ahead.
Well, I actually had a question about that negate
Mm-hmm.
function. I was going to ask you, because I also had some other questions about 4 through 16. But, so if you have something that's already negated, if you were to then negate that, would it return that as a positive?
Yeah, so negate is basically like multiply by -1.
Gotcha, okay. Yeah,
So if
I
it...
was going to ask about these ones where it asks us to use literals to do various things.
Mm-hmm.
I just wanted to make sure that, so the literals, that's for the actual act of incrementing it. We can still use things like, MOVWF.
Mm-hmm. Yeah, yeah.
If we're going to have multiple lines.
Right, definitely.
Okay, just making sure, because I use some of those.
Yeah, the goal of those questions was to use at least one instruction that involves a literal to help you do what you're trying to do.
Gotcha, yeah, and I wanted to know about the negate one because that's how I answered number 17, was I used negate basically to
Okay.
reverse, because it says in the instructions, I don't remember what the command is, I think it's the subtract W, SUBLW. It says that it subtracts, shoot, I don't remember which one it is.
So subtract literal W is kind of backwards.
Yeah.
Right, it subtracts W from the literal instead of the other way around.
Yeah, and that would leave you with a negative result.
Yeah, that would leave you with a negative of what you want. So then you could use negate to flip it around to what you do want.
Yeah, exactly, and that was the answer that I gave.
Cool.
I wanted to know if that was like a valid thing you could do.
Yeah, absolutely.
Okay, thanks.
All right, you're welcome. So while we're opening cans of worms, let me toss another thing out there, and I don't like putting this out there too soon because it's easy to sort of like abuse this. But someone noted in Tuesday's class when we were looking at the special function register that WREG itself is listed as a special function register. And it is. It's I don't know, F86 or something like that, some number I can't remember. But it's, WREG is just another special function register. And so it's perfectly legitimate to do something like negate file WREG. Yeah. Wow. Right? Negate file, and we have to specify a file register. We can specify the file register called WREG. And this will take the current value of W, multiply by -1, put the result back in W. If we want to increment the W register, we could say increment file register WREG. That's going to be the same thing as adding literal 1 to W. And so if we wanted to decrement W register, we could actually do it with the command decrement file WREG. That's another option. But be really careful with these, right? WREG is not the same as W, right? W is just a shortcut for 0. So if I say increment file register hex 80, comma W, that means read the contents of this file register, add 1, and write that new result into the W register. If I put WREG here, all heck breaks loose. Okay, or if I say increment FW, that's going to do some really crazy things. That's going to increment file register 0, because W means 0. So you got to be kind of mindful when you're doing assembly language of what exactly you're writing. C, we kind of get in the habit of just writing whatever we want, and we compile it, and if we did something wrong, we'll usually get a compile error, right? Assembly language, very few things that you might do wrong will actually give you an error, right? If I say increment FW, that's going to assemble just fine. But since W is set equivalent to 0, this is going to say increment file register 0. And that's probably not what I meant when I wrote increment FW. Someone said it's crazy to me how people did this manually with punch cards. This is almost easier with punch cards, actually. The thing with punch cards was it kind of forced you into a different mindset. And you could actually hold your code in your hand, you know. And each line of code was a card, right? A big piece of cardboard. And it kind of slowed you down. It forced you to kind of go through things more, you know, line by line. And it was also nice for editing because you could be, you know, completely away from a computer, but you could, you know, take a pencil and make changes on your punch cards. And the punch cards had a little corner cut diagonally on one side. And so if you made a change on a card, you could flip the card over in the deck and you'd get a corner sticking out. And so you could find your changes quickly. And there's all kinds of things that you would do that that let you do pretty efficient, you know, editing and review and manipulation of programs on these Hollerith cards. And like I say, it kind of forced you to slow down, and you couldn't, you know, accidentally delete 100 lines of your file or make some random change without realizing it, and so on. And you had like physical backups, you know, if you had your code and you changed something, well, you had the old card that the old code was on, you know, you could go back to it. So it was actually kind of interesting. It had some advantages. But man, can you imagine writing like, you know, a few gigabytes of code on punch cards? All right. Yeah. So other questions? All right. Let's go ahead and send me an attendance check. So let me know. Let me know that you're here. And let me just mention, I don't think I have a link to this on Canvas, but you can find this through Google. Look for documentation on MPASM assembler. It's a fairly hefty document, but you know, this is the documentation for MPASM. And if you want to know about, you know, what exactly the EQU statement does, well, there's you know, it's described in the documentation. So this is on page 105. I've never looked at this before. So EQU, define an assembler constant. The value of expression is assigned to label. So it doesn't tell you in here what EQU is, so we can make it up. But you know, if you want to know about some of the specifics of these things that we do in our assembly code, you can go to this document. and find answers to all of that. And you can find lots of other things you can do. So number sign define, is one way to define a symbol, but there's lots of other things we can do in the assembler. We can make macros and things like that. So if you want to dig further into your code, there's possibilities like that. All right, so let's continue with our fish tank example. And the goal here is I want to look at how we take individual bits, right? When we put 5 volts or ground onto a pin, or we take a pin and we hook it up to a motor, we're dealing with single bits, right? I want to set this bit to a 1 to turn this motor on. I want to read this bit because that's coming from my button labeled attention. And I want to look at how we can study individual bits in this world where we're forced to do things an entire byte at a time. Port A is a byte. Increment file register operates on a byte. Things like that. So I'm going to use this example of a PIC-based fish tank controller as a way to dig into some of these operations we're going to do. So let me set this up again. So pin 8 is going to be connected to a sensor which says the water is too hot. And pin 9 is going to be connected to a sensor which says the water is too cold. And our heater is going to be driven by the output on pin 17. And so if we look at these, so pin 8 was RB0.
Bless you.
Bless you. Pin 9 was RB1.
Sorry.
Oh, you're good.
And pin 17 is RB2. All right, so first thing we want to think about is TRIS-B. So TRIS-B is 8 bits. And each bit of TRIS-B corresponds to a bit of port B. Right, now RB0, RB1, RB2, these are coming from port B. This is bit 0, bit 1, bit 2. All right, so magic question. If we want to specify a bit to be an input, do we set the TRIS bit to be a 1 or a 0?
1.
Set it to be a 1. So RB0 should be an input. We want a 1 right here. RB1 should be an input. We want a 1. RB2 should be an output. We make that a 0. And at this point, we don't really care what's in these other bits. We just care about those 3 least significant bits. So as we're running our code, we're going to do some setup. We're going to set up TRIS-B. We'll have to do some other setup that we'll talk about in a bit. But our main loop could look something like this. Well, we want to read the values coming in on, let's see if this water is too hot. So put a comment in here. Is the water too hot? So how are we going to answer that question in assembly language? How are we going to write code to tell us whether or not the water is too hot? And let's think about it at a higher level first before we get down to individual bits. Just in words, how would we tell if the water is too hot?
We need to check the sensors to see is it above a certain temperature or below a certain temperature.
Okay. And we have a sensor which will tell us if the water is hot, right? This sensor going into pin 8. And we set up the sense for these last week, so 1 equals too hot, 1 equals cold, 1 equals on. So plain old positive logic. So we'd like to read this least significant bit of port B. And if it's a 1, we know the water is too hot. If it's a 0, we know the water is not too hot. Does that make sense? So let's move port B into the W register. Right? Now here's the thing. All we care about is this least significant bit of port B. So let me draw port B here. All we care about is whether this bit is a 0 or a 1. But we're not allowed to just say, you know, let's just copy this 1 bit into the W register. When we say move port B into W, all 8 bits get copied in. All right, now we have 2 possible branch instructions. We have this thing called branch if 0, and we have this thing called branch if not 0. And if you look at a move instruction, move will update that 0 bit, that flip-flop that records whether or not we saw a 0. So we could say, you know, branch if not 0, and we could jump somewhere that deals with the water being too hot. But we're moving all 8 bits into the W register, not just this 1 bit. And really all we care about is the value of this 1 bit. So here's what we might try to write, and this is not exactly what we want. So we could say branch if not 0, too hot. And then somewhere else in our code we could say too hot. And then down here we could say let's turn the heater off. All right, but this doesn't really work. And it doesn't work because suppose this bit is a 0, saying the water is not too hot, but maybe the water is too cold. Maybe this bit is a 1. And so if we move port B into W, W is going to look like, you know, a 1 and a 0. That's not 0. Is this making sense?
Yes.
Okay.
It would evaluate to a 2, right?
This would evaluate to a 2, which is not 0. And so our code here would say, oh, I guess the water's too hot. And it'll go and turn off the heater. Even though the reason it's not 0 is because this second bit is set, which means the water's too cold. So how can we fix this code so that it turns the heater off only if the water is too hot?
Is there a way to truncate the value of port B to just be the singular bit you want?
That would be really useful, wouldn't it? So the suggestion is there some way to basically say, ignore all of this and just look at this 1 bit? So anybody got any ideas how we could do that? This is a huge concept we're coming up to.
Where you like cut it and move it to the front using, I don't remember what it was called.
Rotates?
Make it the most significant bit.
We could do something like that. That would work well in this case, but it may not work in other cases. So let's keep that one in reserve. But let's see if there's another way we can do this.
Can you pick out? Go ahead.
Couldn't you rotate right and look for the carry bit?
We could rotate right and look for the carry bit. And again, that would work well in this case because we're looking for this bit. But suppose we were looking for a bit sitting over here, for example. right? Then we would need to rotate a bunch of times. So that's also going to work, but I'm going to hold out for another approach. And let me put this out there. When we think of this on paper, we can say, let's ignore these bits and let's just look at this bit. Okay? That's not an option for a computer. It can't just ignore these bits. But the next best thing might be, what if we forced all these bits to be zeros? Right? What if, even if there's a 1 here and there's a 1 over here, what if we could change this to look like this? 7 zeros, and then this bit down here is either a 1 if it's too hot or a 0 if it's not too hot. If we can do that, we've made our life a little closer to what we like thinking of, which is thinking about things in terms of bytes instead of bits. If we can change all of these bits to become zeros, now we can interpret port B in one of two ways. If port B looks like this, it's too hot. If it looks like this, it's not too hot.
I'm looking through the bit file register operations. I don't know if you'd be able to use them because they're for file registers, but if you could use them for the special registers, you could, I think, use a bit set on the first, on the last 7 bits, and then a bit toggle if the too hot returns true.
Okay.
Toggle first bit, right?
Yeah, that's a lot closer. So we can use these bit instructions. We haven't talked about those yet, but there's bit set and bit clear and bit toggle, and we can use those to manipulate individual bits. But let's go even simpler than that. Let's just use the instructions in the beginning of that table. Is there some way to change these bits to all be zeros, other than setting each one to 0 one at a time? So this is an Engineering 250 flashback.
You just clear it?
Well, almost. If we clear a file register, all 8 bits will go to 0. But we want to just clear the upper 7 bits.
Maybe swap?
There's cases where swap will help us with this.
We could set the first 7 bits with bit set and then XOR the last bit, maybe?
That would probably get us there too. But I'm trying to avoid having to do multiple setting or clearing of bits one at a time. These are great ideas. And all of these will work. But I'm holding out for a different solution which is going to work in a lot of different situations. But these are all good suggestions that would get you there. Think about logical operations.
Maybe the rotate command?
Rotate will come in a little bit. But rotate will preserve your bits, so if we have, 1s and 0s over here, they'll still be part of our file register after we rotate.
Is it compare SEQ? One of those?
I'm not going to touch the skip instructions yet, so compare and skip if equal, compare and skip if not equal. I'm going to stay away from those for a few classes. And same thing with bit test and skip, which would also work for this.
Could you also just move the file so it reads a 0 to reg temporarily and then move it back in afterwards?
We can move it to set those 0 bits, and that is something we're going to want to do before we do the branch if 0, branch if not 0, maybe. But we've still got to get rid of suppose our file register looks like this. And we want to change it to look like this. But if our file register looked like this, then we want to change it to look like this. The result is, you know, this is 0. This is not 0. And it's 0 because this bit and this bit alone was 0. This is not 0 because this bit and this bit alone was not 0.
Okay, I think I get it. Use and 1.
Cool. So if we were to take this number and we were to do a logical AND operation, so let's suppose this is in the W register, and we AND it with the following literal. All right, so go back to 250. Think about an AND operation.
Oh, that would work.
And when you look at your truth table for an AND, if we just think about the second bit that we're ANDing with, anytime you AND with a 0, you end up with a 0. But anytime you AND with a 1, you end up with the bit that you started with. So x ANDed with 0 is equal to 0. X ANDed with 1 is equal to x. And that's something we can use. Because if we AND these 7 bits with zeros, we'll end up with zeros. And if we AND this bit with a 1, we'll end up with that bit. So let's look at a number in terms of its 8 bits.
So in context, we would have to move it to reg and it with that specific number in reg, and if it then read in reg that specific number, then it would change?
Yeah, so take your number and it with this bit pattern, and if so let me write this out. Right, this is the number you'll end up with. So now we can do our conditional branch. We could say branch if not 0. And the only way that this is not going to be exactly equal to 0 is if bit 0 is not 0. In other words, if this was a 1, if that was a 1 right there. In other words, if our hot sensor was saying, hey, the water's too hot. So we can say branch if not 0 after we've done this, and that says it's too hot. And this is something you're going to do again and again and again. And every time I've taught this course, this is one of the 4 or 5 big things that people stumble with throughout the entire course. And so I'm spending time. Normally I just brush over this, but I'm spending a good chunk of this lecture trying to develop this, because if this makes sense to you, everything that we do in the second half of the course is going to be so much easier. because we just do this again and again and again. And Lab 2 requires you to sort of understand what's going on here. And so this is time well spent. So this is a trick we can use if we have a number and we're only interested in certain parts of that number. We can force the uninteresting parts to 0 by ANDing with something that has zeros where those uninteresting bits are. And so if we were to translate this into code, we might do something like this. Move file register port B into the W register. And the W register with the following literal. And then if the result is not 0, go down to our section of code that handles with the water being too hot.
So, quick question.
Mm-hmm.
Like in C and other languages like that, if you wanted to use binary, it'd be 0B number, or kind of like 0x is hex.
I don't know if C lets you do binary like that. In MPLab, it's just B, single quote, and then the bit pattern, and then a closing single quote.
C will let you do binary like that, and
Yeah.
so does Python.
Okay, cool. And you know, in this number written in binary, well, it's really just a 1. We can just do a 1, but it's sometimes more clear, especially when you go back to your code later, if you're using an 8-bit pattern to actually write it out as an 8-bit pattern, right? Even though we could just write a 1 and it's exactly the same, or we could write 0x1, right? The way you write it is uninteresting to the assembler, and it's meaningless to the actual processor when it's running your code. But writing it like this, you know, to me makes it clearer what I'm doing. I'm interested in an 8-bit pattern here. And then if I follow this with more code, which says something like this. So let's move port B into the W register, and then let's AND it with this bit pattern. Well, now I'm picking off this bit, right? I'm putting a 0 here, but I've got a 1 here. So this bit's going to be bit B1. And that bit corresponds to the value coming from my cold sensor. So now if that's not 0, I can branch to a section of my program that says, hey, the water's too cold. And in that section, I'll turn the heater on. All right, questions about this?
So, too hot, too cold, and this case would just be other modules in your code that you're...
Yeah, I'd have a label somewhere that says too hot, colon, and in there I'll write some code to put a 0 into bit 2 of port B. And the section that says too cold, I'll write some code that puts a 1 into bit 2 of port B to turn the heater on. Alright, so this is a general concept. This is called a bit mask. So this pattern here that I'm using to do my logical AND operation, that's called a bit mask. And if you've ever played with spray paint, like a stencil, right? You want to spray paint a pattern, you take a piece of cardboard, right, and you put it over something, and you spray the whole thing with spray paint, but where the spray paint hits the cardboard, it doesn't go through to the surface underneath, right? That stencil is like a mask, when you paint trim on a wall, right, you get tape, used to be called masking tape, and you stick that along the spots you don't want painted. And now you can just slop paint, you know, on the wall, over the trim, but the places where you don't want that paint to go don't go to the wall, they go to that piece of tape. Well, this is like a mask for bit operations, right? When we AND something with a 0, it wipes it out. It changes that bit to a 0. But this little 1 right here, right, stops this bit from being changed to a 0. It preserves it. So we're kind of like, you know, taking a big eraser and running it over all of our bits, but we've got a mask over this bit B1 right here. So we run our eraser along, all of these bits change to 0, but this 1 bit is preserved. And now we've got a nice clean number with zeros everywhere except for the bit that we're actually interested in. And that lets us now ask a much simpler question, which is, hey, this new number, is it exactly equal to 0? If it is, we know that that bit that we preserved was a 0. If it's not 0, we know that bit that we preserved is not a 0. It must be a 1. So a bit mask is a general construct we use when we're interested, in this case, in one particular bit inside a byte. And we want to scrub away all the other bits and just look at this 1 bit. And like I say, we'll do this a lot, and you're going to do this extensively in Lab 2. And we'll go through the details of Lab 2 in a little bit, and we'll see how to use this. But I want to develop this idea a little bit further. All right, so let me add some extra stuff to our fish tank. So I'm going to use a pair of bits 4 and 3 of port B, and these are going to be a 2-bit number, which represents the temperature on the left end of the fish tank.
Could you, if you wanted to, define one of those bit masks to be used, like, hey, I need a bit mask to mask everything with this bit, you could define it, right?
Mm-hmm. Yeah. Yeah, and the simplest bit masks are, you know, usually just one 0 with, or a single 1 with zeros everywhere else, like this one. But we'll see some more complex masks in this next example. So in my fish tank, I'm going to put a pair of temperature sensors, one of them over here and one of them over here. And each of those sensors is going to generate a 2-bit temperature reading. Okay, this is going to be called temp left, and this is going to be called temp right. And they're 2-bit numbers, so they look like this. And you know, this is I don't know what water a fish tank temperature should be at. Let me just say this is 70 to 72 degrees. This is 72 to 75 degrees. This is 75 to 78 degrees, and this is 78 to 80 degrees. It's just a goofy example. So we've got these fancy sensors we put in our fish tank, one on the left end, one on the right end. And each sensor feeds up a 2-bit piece of data telling us what the approximate water temperature is at that point in the tank, anywhere from 70 to 80 degrees, and it's a 2-bit number. And these 2 bits for the left sensor, those go right here. So this is temperature left. And the 2 bits from the right sensor go right here. This is temperature right. And we're also going to have an alarm. And so that's going to be this last bit of port B is going to be an alarm. And if we write a 1 to that bit, some alarm will turn on. And it'll like ping our phone or something. All right, so here's what we're going to do, because this is a super fancy aquarium we're building now. We're going to look at the temperature reading on the left and the right, and we're going to compare them to see if they're equal. And if they're not the same temperature, we're going to sound an alarm. And we're going to say, hey, the water's not circulating. All right. So we're going to have to change our tri-state register. We're going to want to read from the sensor on the left and read from the sensor on the right. And we're going to want to write to that last bit position because that's the alarm. So our tri-state B is going to have this bizarre pattern, 0, 1, 1, 1, 1, 0, 1, 1. And our code is going to look something like this. So let me write this out. Let's read port B. And then if bits... And so the temperature left are coming in on bits 4 and 3. So I'm going to write this format. Angle bracket 4:3. That's a notation that you'll see a lot in assembly language. It means just take bits 4 through 3 and treat that as a number. So if bits 4 to 3 are not the same as bits, our other sensors from 6 and 5, bits 6, 5, turn the alarm on. Else turn the alarm off. And go back in loop. All right, so you understand what we're trying to do here? Usually when someone asks why it's 4.3 and not 3.4, so this needs to be specified. So in your system diagram for this sensor, this would go into RB4, this would go into RB3. This would be temperature left. I'm going to call this the most significant bit. This will be temperature left, and this is the least significant bit. So we had a little table here, right? Well, how do we know whether RB4 is a 0 or a 1 in this case? How do we know if that 0 is RB4 or RB3? How do we know if this 1 is RB4 or RB3? It's got to be specified somewhere. So you know, there's a piece of paper that comes with this sensor, and it will tell you, you know, this wire is the most significant bit, this wire is the least significant bit, and then you would decide, okay, I'm going to hook the most significant bit up to RB4 and the least to RB3. Well, if that's the case, then I'm going to refer to this 2-bit number as angle bracket 4:3. So this is most significant bit, least significant bit. It's just kind of a convention. But it could be different. It could be that the most significant bit is bit 3, and then it would be 3:4. Yeah, if they were switched, it would be 3:4, exactly. And almost always today, when you break things up into fields, when you're using part of something, part of a byte to mean something, usually the most significant bits are to the left, and the least significant bits are to the right. And when you use this angle notation, we're always specifying the most significant bit and the least significant bit. And if you go through the data sheet, you'll see this on some things where part of a field is significant. You'll see this notation. All right, so we want to write code that tells us whether the 2-bit number in bits 4 through 3 is the same as the 2-bit number in bits 6 through 5. And we could do that a lot of different ways with a lot of if statements and so on, but let me show you a fairly straightforward way to do this. So let's think about our number. And so we're interested in looking at these 2 bits, and we're interested in looking at these 2 bits. And we want to know, are those the same bit patterns? 1 1 1 1, 1 0 1 0, 0 1 0 1, 0 0 0 0. Are these 2 bits the same as those 2 bits? So thinking in terms of words, forget about specific instructions right now. Just think from a higher level. How could we do that? We've got 8 bits. How could we change things around in a way that we can easily tell if these 2 bits are exactly the same as those 2 bits? What kinds of things could we do?
We could store it in a file and then rotate it to the point where we could have 4 and 3 at the end. Bitmasks it to where 4 and 3 are isolated at the end. And then you can take the original file you had stored of what it is now. So then you can take it again and rotate 6 and 5 all the way to the end and store that in a file and then compare the 2.
All right. Did everybody catch that? This is
That was a lot.
that is a lot. So let me go through that. So the key here is combining rotates and bit masks. So suppose this is our original number. So let me call this a file register named temp. Right? So rotate right 1 2 3 times. All right. If we rotate this number right 3 times, then these are going to be the 2 least significant bits, followed by this, followed by bit 7, and then bits 0, 1, and 2. Right? It's just going to move everything down. This will be the rightmost side of our number.
Would it be just a regular rotate or rotate with a carry?
I would do a rotate with no carry.
Okay.
Although I don't think it's going to matter. But basically we want to shift this thing down 3 spots. And then we could AND with this bit pattern. And so let me call these things, well, let's just write this out in all its glory. Let's start with our number B7, B6. Okay, so let's rotate right, no carry F 3 times. And so this is going to end up looking like the following. And then if we AND with this bit pattern, we're going to end up with the following. All of these bits up here get cleared out to 0, but those last 2 bits, B4 and B3, those are saved. And so let's save that in, let's just call it a variable temperature left. All right, now do the same thing. do a rotate right 5 times. And now this is going to look like this. Or you could rotate left 3 times, same thing. And now, and with the same bit pattern, and you're going to end up with all of these upper bits being changed to zeros, and these 2 lower bits are preserved, and we can save that in a register called temperature right. And now we're all set. We've got basically a 2-bit number for the left temperature, and we've got a 2-bit number for the right temperature. So I don't know, we can put this in a temporary, we can subtract that from it, we can see if the result is 0. And if you want to know if A is equal to B, well, a similar question is A minus B equal to 0? So we could take temperature left, we could subtract temperature right, and then we could say branch if 0. And if the result is 0, we know these 2 temperatures were the same. In other words, these 2 bit patterns were identical. Basically, isolating each pair and then comparing them. The bit mask is to remove any other values in the files, and the rotation is for both pairs to be in the same spots. Exactly. So the comment in chat is a excellent synopsis of my wordy explanation. Yeah, that's really all there is to it. And it takes getting used to, but you will find so many uses for this, because particularly on RISC machines, right, things inside tend to be very bit specific, but our instructions are byte oriented, and we constantly find ourselves taking apart bit patterns and putting them together in different ways. All right, cool. So chew on that for a few minutes. So 3 things. First, send me another attendance check. Let me know if you're here. And then we'll take a 5-minute break. And then let's start talking about Lab 2. And we'll talk about using these concepts in Lab 2. And we'll talk about flowcharting to organize our thoughts on the code that we're going to write. And that should leave us in good shape. All right, so we will come back in about 5 minutes. Let's see. There we go. All right, we're back. So let me make some comments on flowcharts and flowcharting. So part of the requirement on lab is to document your code, and I mentioned, the lab says you can do this with pseudocode or a flowchart, but I'm requiring you to write flowcharts. Okay, so flowchart is a graphical or visual presentation of your algorithm. And I don't know if you do a lot of this in 121. We do some of it in CSE 120, Engineering 120. But it's a useful skill, and it's really useful in assembly language, because assembly language, we do branches where we have these arrows that go back up to the top, and flowcharting goes back to a time when we wrote code with lots of go-tos and if statements, and not a whole lot of for loops and while loops. So let me just do a quick review on flowcharting, and then let's look at how we would use that for our fish tank, and then we can apply that to lab too. So pretty straightforward. Basically, something with the word start and an oval, that's the beginning of our program. And we have a few different kinds of blocks, really two different kinds of blocks. A rectangle is where we're going to do some fixed thing. So, initialize tris B, port B, initialize some flags, or whatever, right? And we can put one thing in a block. We can put multiple things in a block that kind of belong together. It depends on how we want to write this, but rectangles basically have things that we want to do. But then there's decision points, and so we can draw a diamond, and we can say, is x equal to 1? Or is this flag true, or is this bit equal to 0, or are these bits equal to those bits, or something like that. And we can have a side labeled yes and a side labeled no. And maybe our no side just goes on to the next statement, and maybe our yes side does, something. Maybe does a few things. And then, at some point might come back to this main branch of stuff we're going to do. And then maybe somewhere down here, we go back up to, somewhere else. And so our flowcharts look like this, right? And basically, we begin at the start, we read from top to bottom, but when we come to one of these diamonds, there's a condition inside, and we have, two branches coming off of it that tell us which way to go, depending on whether that condition was true or false, or whether the answer to the question is a yes or a no. And, if our code exits at some point, we can have, something which says end. But most of our assembly language code never ends. It's always going to loop. It's going to go back and just keep doing something over and over. There's no really such thing as an end on a microprocessor. Unless maybe we halt the processor or something. So is this something you've seen before, at least in 120?
In textbook, but this was never practiced.
Okay, so this is a good chance to practice it. And it's really meant to help you organize how you're going to implement an algorithm, because in C, if we want to do this, this, and this, we can just write a statement for this, another for this, and another for that. In assembly language, this diamond right here might be, 4 or 5 or 10 assembly language statements. And when we're writing the assembly language, we want to be clear, as we're writing it, what are we trying to do? Oh, we're trying to see if x is equal to 1. Alright, so I gotta take X and I gotta put it into W and I gotta subtract 1 from that somehow, and then I gotta see if the result is 0. And if it's 0, then I want to come over here to where it says do stuff, because that means that, you know, X minus 1 was 0. And you can definitely do flowchart and pseudocode. In fact, I recommend doing both. Pseudocode probably at the highest level, and then flowcharting at a lower level with more detail, and then assembly language when you're actually writing, you know, the instructions for it. So it can be tricky trying to understand how detailed we should make a flowchart. So let me work with our fish tank example. And in pseudocode, what do we want to do, right? Initialize stuff. So tris_b and some other stuff. Is it too hot? Let's say if the water's too hot, turn the heater off. If the water's too cold, turn the heater on. If temperature left is not the same as temperature right, set alarm on. Otherwise, set the alarm off. And let's just go back up here and loop. Alright, that's decent pseudocode, right? That just kind of helps me understand the highest level behavior. Check the temperature to see if it's too hot. If so, turn the heater off. If it's too cold, turn it off. Turn it on. If the left and right temperatures aren't the same, we've got a water flow problem, so let's turn the alarm on. Otherwise, turn the alarm off because the water is flowing fine. And let's just go back and keep doing that forever. So this would probably be the first thing that I would write. But now if we want to make that into a flow chart, we get a little more detailed. So initialize tris_b. And there's one other thing we'll have to initialize. We'll see that in a minute. But now I'm going to want to know if my temperature is too hot. Well, how do I do that? Let me find my magic fish tank diagram. There we go. So too hot, I want to check bit 0 of port B. So I would say something like this. Let's look at bit 0 of port B, and let's see if it's equal to 1. That's the situation where it's too hot. So if it's yes, let's put a 0 in bit 2 of port B. And if we don't have a sensor saying that the water's too hot, then we don't have to do anything. And now we can say, is the water too cold? So bit 1 is the cold sensor, and if yes, that bit's equal to 1, then we want to turn on the heater, so we put a 1 into port B, bit 2. Otherwise, we go on. And if I'm running out of space, I'm just going to put a little circle with an A here, and I'll continue on the next page. My little circle with an A. And the last thing I want to know is, are these temperatures the same? The temperatures on these 2 bits and the temperatures on those 2 bits. So I'm going to make a bigger diamond. Let's see if port B 4.3 is the same as port B 6:5. And if not, then I'm going to say, let's sound the alarm. So let's put a 1 into port B, and the alarm bit is bit 7. But if these two values are the same, then I want to turn my alarm off. So I'm going to put a 0 into port B, bit 7. And then I'm just going to continue. And I think at this point we've done everything we need to do, so here we would just go back up to the top up here. So something like that. All right, so why do we want to do this when we've already got pseudocode? Well, you know, when we're trying to write these if statements, this is going to take multiple statements in assembly language. And you know, here we've got a situation where we're checking to see if something's equal to 1, and if it is, we do something, but if it's not, we don't have to do anything. Here we're checking to see if some condition is true. If it is, we do something, but if not, we don't do anything. But here we're checking some condition. If it's true, we do one thing. If it's not true, we do something else. This is like an if-else, whereas this is just a plain old if. And keeping that straight, because we're taking this flowchart and mapping that into assembly language, that's going to be less error-prone than trying to do this in our head, right, straight from the pseudocode. And then when you're running your code, if your code's not working, you can follow along as you step through the simulator. You can follow through with your finger. Okay, so I just found out that this bit's a 1, so I should come over here, and when you step the simulator, it should go to a section of code corresponding to this. And if it doesn't, then you implemented something wrong in this part of your assembly language. So you want your pseudocode and your flowchart written out and nearby when you're debugging your code in the simulator. And yeah, you know, once you're very fluent with all of this and you're very comfortable with coding, you know, if statements and loops and so on, we find we can eliminate the flowchart and we can just work with the pseudocode. But for now, I want you to definitely do the flowchart. And this is probably a reasonable level. Right, I'm very clear here. I'm comparing bits 4 and 3 of port B with bits 6 and 5 of port B. I don't really want to clutter up my flowchart with move port B into temp 1, rotate right 3 times, move it into W, and it with this bit pattern, because now I'm just taking my assembly language and drawing it inside rectangles and diamonds, and that's not going to be as useful when I'm developing and debugging my algorithm. So part of the challenge here is figuring out what level to put things at, right? Let me show you a flowchart that would be much too high of a level. Right? Technically, that's a correct flowchart for our system. But this does not tell me how to do these things, right? The distance from here to the assembly language is very great. Whereas the distance from here to the assembly language is not so large, right? Now, yeah, I need to use a bit mask here. I need to use a rotate and a bit mask here, right? But find a level that makes sense to you so that you're capturing kind of the higher level behavior here, but not, you know, so super high level that it doesn't really tell you anything. And there's an item on Canvas, I believe, I put up on finding the right level for pseudocode. And it's a similar challenge with pseudocode, right? Do you put in like the assembly language instructions, or do you put in, you know, something super high level like this, or do you find something kind of in the middle? So explore that, play around with that. That'll be a part of Lab 2, which we will look at presently, and just keep these things in mind. All right, so let's take a look at Lab 2. So I want this on a different page anyway. All right, so lab 2, we're playing around with input-output. So a lot of the beginning of this lab is a repeat of things we've been talking about. So the pin out of the chip, which isn't too concerning to us, how you apply power. The notion of the tri-state registers, tri-state A, tri-state B, correspond to port A, port B. There's one other setup that we have not talked about yet, and that's something called ADCON1. And without getting into details of this, any time that you're doing any I/O on the system, in the very beginning, you want to put hex 7F into ADCON1. We're just going to do that. We're not going to worry about it. Okay, it's just something we do. It's like brushing your teeth before you understand tooth decay. Get up in the morning, you brush your teeth. Start your program, put 7F into ADCON1. And it's 2 instructions, right? Move literal 7F into W, move W into ADCON1. So put that in the very beginning, you don't have to worry about it. A lot of people like clearing your ports before you use them. I don't think that's necessary, but it doesn't do any harm. And then you want to set up your tri-state register to say which pins are inputs, which pins are outputs. So you'll always see in the code, in the labs, in the code, in the text, you'll always see in the beginning of your code, clearing a port, putting 7F into ADCON1, setting up a tri-state register. If we're going to do port B, you'll see a clear of port B, and you'll see a loading of tri-state B. ADCON1 only has to get set up once. Just put a 7F into ADCON1. So this talks more about the tri-state registers and how the 1s and 0s relate to inputs and outputs, right? 1 makes the bit an input, 0 makes the bit an output, and so on. We're not worried about the watchdog timer. So experiment 1, 4-bit adder. So what's the goal here? We want to make our famous 2-bit adder. Okay, so this was our, oh no, it's a 4-bit adder. Cool, we changed it. All right, so we're going to make something that adds 2 4-bit numbers. And our numbers are coming in on port B. And the first number is in bits 3 through 0. Bit 3 is the most significant bit. The second 4-bit number we want to add is coming in on port B, and it's bits 7 through 4. And we're going to get a sum of those. Well, if you add 2 4-bit numbers, what's the largest number you can get? What's the largest sum of 2 4-bit numbers?
A 5-bit number?
It's a 5-bit number. What's the biggest 4-bit number we have?
16 or 15.
Yeah, the largest 4-bit number is 15. And if you add 15 to 15, you get 30, and you need 5 bits to represent that. So your setup here looks like this. These 4 bits give you the first number. These 4 bits give you the second number. You're going to calculate your sum, which is num1 plus num2. And then you're going to write that out to port A. Into these 5 bits. And I would just throw zeros out there because it makes things easy to see. Right? And then we're going to loop. So we're going to repeatedly read port B, break it up into 2 4-bit numbers, add them together, put that sum out to port A. All right, that's the whole labs, one experiment. And so you can see where the things we've been talking about are going to come into play here. We're going to read port B, maybe you're going to copy it into the W register. Well, in order to add two numbers together, right, we don't have an instruction which says add these 4 bits to those 4 bits. But we do have an instruction which says take this file register and add it to the contents of a W register. So you're going to want to do something like the following. Yeah, you're allowed to use adding operations. Don't try.
Swap F?
You can use swap F, or you can rotate 4 times. So yeah, you might do something like this. Take your value that's in port B, and it with a bit pattern that looks like this. And that's going to change these bits to be zeros. It's going to leave these bits intact. Now you have an 8-bit number that is, the same integer value as num1. So save that somewhere. Put it in a variable called num1. And now take your value from port B, copy that into a temporary, and maybe do a swap, right? Which would put num2 down here and num1 up here. Or a rotated right 4 times, or a rotated left 4 times. But change this around so that you have num2 sitting down in these positions, and that with a bit pattern. And now you've got a nice number that looks like this. 4 zeros followed by the 4 bits of num2. And save that in another file register called num2. And now you got a nice simple pattern, right? You've got a register num1, register num2, you want to add them together. So copy one of them to W, and then add W to num2, or whatever the other one is. And if you save the result in W, W is your sum. And now just copy that out to port A. Move WF port A. And there are a lot of different ways to do this, right? You can put your number of interest into these low 4 positions and then AND with this bit mask. But you could also take this 8-bit number and AND it with a bit mask that looks like this, to leave num2 here and change these to zeros, and then do a swap F, which would bring you back to this. There are lots of different ways to do this, but do something that makes sense. And exercise this code in the simulator, right? And break it into pieces. Let's say you just want to take your port B value and break it into num1. Well, write some code to do that, and then step through the simulator and see if it works. And then add the code to take num2 and turn it into this, and step through the simulator and see if it works. And by the time you got your final piece of code written and you test it, it's almost 100% guaranteed it's going to work, because you've been testing each of the pieces as you've been developing them. Right? So don't just write the code and then run it for the first time after you've got, 60 lines of assembly language written. Really hard to debug. Right? Build it up in pieces. If you're a CS student, we get to 224, 22, 23, we're going to be hammering this point again and again and again. Break your code into small pieces, develop these small pieces, and then put them together to make bigger pieces. Test those bigger pieces, put those together to make still bigger pieces. So at the end, when you've got your final program, guaranteed it's going to work. And the problems that come up along the way, and we always introduce bugs when we write code, but the bugs that we introduce along the way will be introduced into a very specific section of code, and we'll be able to focus just on that one section and find our bugs pretty easily. All right, so that's some Lab 2 details. All right, two other specific details on lab 2. One that's described in the documentation, one that's not. So the first detail is the program shall wait until the values of the operands change and only then update the sum. Okay, this doesn't affect really the way that your code looks from outside, but it's an important nuance that we want to see in your code. So if I were to write this in pseudocode, I would do something like this. So, you know, initialize stuff, which, you know, would be set up the tri-state A register, set up the tri-state B register, set up addcon1. So initialize stuff. Set num1 equal to port B 30. Set num2 equal to port B 7 through 4. Set the sum equal to num1 plus num2. And then copy that to the port A. And then go back up to the top. Alright, but there's an extra step we need. So with a loop that checks to see if it's changed, and then it does do the addition work. Yeah, exactly. But so how do we know if it's changed? Well, in pseudocode, I might say something like wait till port B changes. Because if one of your operands change, then port B is going to change. All right. Well, how do we do that? It's a little trickier than it sounds at first. All right, make yourself another file register. So someone said, can we copy port B into WREG? Yeah, but let's not use WREG. Let's just make another file register called previous port B. Right. So somewhere, you know, our code will say previous port B. I don't know, we'll store it somewhere, hex 20, some file register. But here's the logic we can use, right? Is port B the same as previous port B? If it is, then let's just go back up to the top here. All right, we're going to compare port B to see if it's the same as the previous port B. And if it is, we'll go back up to the top. If it's not, then first thing I'm going to do is take the current value of port B and copy that into my previous port B. And then I'm going to go ahead and I'm going to break my port B into num1 and num2. I'm going to add them together. I'm going to copy that to port A. And when we're all done, we're going to go back up here to the top. So really all I need to do is add this little section at the top of my main loop. And if port B changes, right, I'll take the current value of port B, I'll save that. I'll add my numbers together, put that out to port A, And then when I come back up here, I'll say, is port B the same as that thing that I just saved? Well, if B hasn't changed, then yeah, it's going to be the same. I'm just going to sit here and I'm going to spin in this little loop up top. But now if you toggle one of the input pins on port B will be different from previous port B. I'll fall through to here. First thing I do, save the current port B into this temporary variable. Go ahead and break it into num1, num2, add them, put it out to port A, go back up to the top, and now I'm going to sit here and spin until port B changes again. So that extra embellishment of only change the outputs when an input changes is really just adding this little check up here and then saving port B to previous port B. Does that make sense? Cool. All right, there's one more nuance that I will warn you about. So it's tempting sometimes to do something like this, but I'll say don't do this. Suppose, you know, port B looks like this. This is num2, this is num1. And I want to put num2 into, you know, a file register called num2. I want it to be down here. So I could do something like this. Swap F, port B. So swap those around. Move F, port B, W. And W with the literal, and then move W into the file register num2. And at first glance this may make sense, right? We'll swap the fields around here to put num2 down here, we'll put that into W, we'll AND it with this bit mask, and then we'll copy that into num2. And this totally will not work. So the question is, what's wrong with this? Why doesn't it work?
You can't swap them because they're a special memory address. They're for pins.
We can't swap them, right? This swap instruction does not do what we would like it to do. Right? To us, you know, we're the programmer. We get to control what happens. To us, this should just take these things and swap them around. But port B is not a general purpose register. The way port B is set up, RB7 goes here, RB6 goes here, and so on. RB0, right? This is a physical pin on the chip. This and this are physical pins on the chip. We can ask the processor to swap these around, but it's not going to rewire the hardware inside the chip. When I read port B down here, bit 7 of port B is still going to be coming from the pin labeled RB7. Same thing if I you know, could do a logical AND operation with port B directly with some mask, it's not going to drive these inputs to be 0. Right? These are always coming from the pins on the outside of the chip. Now, if these are output pins, it's a little bit of a different story. But the way to avoid running into these problems is don't think of port B as a general file register. Anytime you want to do anything with port B, port A, tris B, right? If you want to manipulate the values in those, always copy them into a temporary register and work on that temporary. So if you move port B into WREG and then did a bit mask and then swapped to WREG, that'll work great. That's exactly the right way to do it. And remember the secret trick I told you in the beginning of class, right? The W register is a general purpose register. It's a special function register, but we can treat it. So this is totally legit. right? That takes the left and right nibbles of the W register and swaps them around. That works perfectly. So if I copied port B into W, I could do a swap F on WREG to move these around. I could do an add literal and literal with W to mask out bits and so on. So that's all going to work fine. Just don't do anything that tries to manipulate port B. You can read port B, and if you have output pins that you want to set, you can copy into those output pins. But don't try to basically don't try to do a read modify write. And a swap F is really saying read, modify, and then write back, and that doesn't work. All right, I think that's it for sneaky details. Oh, the other thing, I don't believe this is going to affect anything in the simulator, but in the very beginning of your code, you should always have a statement like this. Config WDT equals off, LVP equals off, OSC equals int IO2. And it's kind of like putting 7F into addcon1. We don't have to worry yet about what this does. But on a physical chip, if you don't put this statement in the beginning of your code, your program won't work correctly.
Yeah, I have a quick question.
Sure.
For, every time I've tried to use WREG with general file purpose functions like swapf, like you just did there, I just get an error every time.
So it has to be uppercase.
Oh, it has to be.
Yeah.
I have a quick question as well. So above the configuration, there's also the RAIDX list. You want that as well to put at the top?
I have no idea what the list statement does. I've been doing picks for almost 7 or 8 years. I have no idea what the list statement does. It doesn't seem to do any harm. So if you put it in, I don't think it causes any problem. But leaving it off doesn't cause any problem either. Radix can be useful if you're not going to put 0x in front of things. And I think the default radix is hex. But I always put 0x in front of things or B single quote in front of binaries. As long as you always specify that, you don't need the radix statement either. But you definitely need the config statement, and you definitely want an include statement, which isn't in Lab 1's code, but you should use it anyway. It saves you from having to do this. And then don't do all of these defines, because those rewrite the values that you got from the include file, and this is really easy to make typos on. So you can define your own variables, but don't define these system variables like port A, tris B, and so on.
Thank you.
You're welcome. And last word would be, when in doubt, take a look at the disassembly listing. You do not have to define addcon1, so addcon1 also comes from that include file. So you don't need any of these up here. Basically anything that ends with an F, something, something, that's a special function register. That's set up for you in the include file. So the only defines or EQUs you need are for variables that you're planning to set up and use yourself. All right, I think you're good to go. So I would go ahead and jump into Lab 1. Come by Lab if you got questions on Homework 2. Homework 2 is relatively short. And some of it works well with Lab 2, but it's using stuff that we talked about on Tuesday. But go through those and come by Lab if you have questions on them. And remember, homeworks are due on Tuesday from this point going forward. All right, I will be switching to my office in a couple of minutes, and I will catch you in there. All right, see. Thanks, you too.
Thank you.
Good luck.
Thank you.